day 3, day 4. Stop for a second. Day 5, day 6, day 7. You're stuck here. Okay. Now, our sun is shining all over the place. Well, you're supposed to be up higher a little bit. Okay, our sun is shining all over the place. And when he shines on our moon, he shines on half of our moon. This entire half of this gentleman is illuminated, as you see. However, what does our Earth guy see? He sees this part of his nice face illuminated. He does not see this part. As a matter of fact, that's when it's at that point of the month, 7 days after the sun and moon separate, what do we see? We see, from the point of view of the Earth, a half of a moon illuminated, shining on that. See? This side is not. Now, as time goes by, we do the same kind of steps. Take another 7 steps, and you'll end up over there. And you take another 7 little tiny steps, and you step right there. And what is the sun, from our earth-bound observer, seeing? The sun is shining on his full face. You can see the man on the moon. His full face is illuminated. An entire round moon appears, the full moon. Halfway around the circle, it's done that. But actually, he really isn't have his full face done. Because this guy has moved a little bit. Have you noticed that? He's not facing full on there. So you've got to move a little bit farther over to be, now your full face is illuminated. Okay, so now let's go step another 7 days like that. Step, 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 step. And now he's over there. Again, part of his face is illuminated. As a matter of fact, if you go outside tonight, you'd see the moon looks like, just a full round side of one and cut off from the other, not a half moon, more than a half moon, because at this point in time, more than just half is illuminated until he gets a little bit farther over, until he's at right angles. Remember right angle square right there between the two lines? And then you would have move a little bit back that way, so you have a right angle between the two lines, and then we have a full half moon. Now let's come step, 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 until we get, until they last meet up again. And what happens now is we can see the back of his head. Stop. Right here, we see the back of his head. What do you see from Earth? Nothing. About a degree a day. And he met up with him after almost 30 days. As a matter of fact, he met up with him after 29 days, 12 hours, 44 minutes, and 3 1/3 seconds. That's what we call the normal time for the sun to catch up. For the moon to catch up with the sun.
Every month it's the same?
Every month it's the same, because we're talking about Mahalach and Tsoy. Mahalach and Tsoy means that you're going at a constant speed in a circle. Constant speed in a circle. Both sides are going at the same speed, so they'll always meet up with each other every 29 days, 12 hours, 793 halakim, which is the same as 44 minutes and 3 1/3 seconds. A halak is 3 1/3 seconds, 3.33333 seconds. Huh? No, but as far as we're concerned from the Earth, and as far as this Mahalach and Tsoy, which is an approximation, the moon is, we're sitting out in our chair in the backyard, watching the sky. It looks like a big shell, and we see these little bugs crawling along there. The moon is moving around 12 times as fast as the sun, and it catches up with it as it goes all the way around. In the process from Earth, we see the moon illuminated in different phases throughout the course of the month, right? That's why we saw a half moon, etc. But all the time the sun is still moving. So really, the moon, he went a full 360 degrees, came here, and then he had to catch up with how far the sun had gone in those intervening days until he finally got there. So now, that's this Mahalach and Tsoy, this idea of 29 days, 12 hours, 44 minutes, 3 1/3 seconds, is the basis for how we calculate the calendar that we use nowadays, because it's based on the approximate, the Mahalach and Tsoy, the constant rate that the two things go around, one after the other. Now, as I mentioned last night, we said that in reality, okay, you guys can actually sit down for a minute. Actually, we'll leave our sun guy standing. Okay, remember, just to review last night, because this is an important point, but I'd like to make sure everybody is aware of it. This idea of the fact that these circles, these perfect circles, that you're going at a constant rate, and constant rate means that once you know constant rate in the circle, how far does it go each day? You know how many days have gone by since a particular time, you know how far he's gone, and if you know where he started, you know then in the future where he is. That is the beauty of the way that the Rambam explains all these things in Kiddush Hachodesh. The real paths of the sun and moon, as they move, they speed up and slow down. And the speeding up and slowing down is very complicated, and mathematically requires a lot of calculations, and a computer can do it very easily nowadays, but the fact is, for people, for thousands of years, figuring all this stuff out by hand is very, very complicated. The Rambam has simplified it so that in 3 prakim a day, in a week, you can go through the whole thing and figure out basically the positions of them. How does he do it? He uses circles, but he uses circles with the observer not at the center of the circle. I mentioned last night that if the observer is not at the center of the circle, I'm over here and he's over there. When he's way out far away from me, he moves each day the same amount for him. For me, it looks like he's moved a little bit less. Okay, that's and that applies both to the sun and the moon. As I said before, I remember, of course, my this device that I invented for the purpose of this class last night, my angle measuring device. Here we go again. This is I have to get a patent for this. It's sold by the millions. This angle measuring device, you've got these 2 pencils. You sight the sun over here. You sight the moon over there. You can see the angle between them. You can watch as the angle increases and measure that angle. It will increase on this Mahalach and Soy at the exact same rate every day. Now, once I go off center, then when I measure the angle over here, as he takes 1 step, I see a big gap. As I measure the angle way over there, as he takes 1 step, it looks like it's smaller. That slows him down over there, speeds him up. Same thing for the moon. All right. The Rambam says, and he brings down, it's actually Gemara, that the path of the sun is Shemesh Adam Voiv. I forgot the exact pasuk, but the Shemesh is fairly easy to understand. All you got to do is move them a little bit off the center like that, and you'll be able to calculate where the Shemesh is if you use these constant speeds, constant rate times time equals distance. The moon, however, is all messed up. And the Gemara says that the Shemesh seems to know which way it's going. The moon, nobody knows what's happening with it. Obviously, somebody knows what's happening because we can calculate. And I read to one of the gentlemen earlier a statement from one of these, from this astronomy book that I have here, which is, this is a graduate level. This is what professional astronomers would use in pointing telescopes and figuring out things to very, very high precision. And I'll just read you this one paragraph that they talk about here. It says the discussion so far is concerned the mean orbit, mean MEAN. You ever heard the word mean? Doesn't mean somebody who's nasty. It means average. That's the Mahalach and Soy that we've been talking about. It says the he says the problem of calculating the moon's apparent coordinates, the actual coordinates of where the moon is extremely complex. The reader who wishes to understand the basic mechanics is referred to such and such books. The basic theory was established by so-and-so at the beginning of the 20th century. So just 100 years ago, they really got it down, so they really nailed down where the moon is. I mean, to extreme precision, much more than we're working with here. There are hundreds and hundreds of different pieces of the equation that describe where the moon is. So when the Gemara says that the calculation of the moon's position is very difficult, it's very, very true. That is very difficult, and it's quite confusing. But we're going to do the best we can to try to get as far as we can in understanding it, because that's what the Rambam says. Matter of fact, the Rambam praises those who are interested in learning this. What is the Lashon he uses in I think it's in Parak. That those people who really want to get involved with it, it's Kol mi sheruchei nechena v'libei tzoy v'divrei ha'koch maslamed al seidus yisava al desire leit arisam adroken shemechash bin behem ad sheyeda adam in Yerah ha'yireh v'leil zeh leira. Okay, so that makes it feel a little bit better trying to go through all the stuff. Okay, meanwhile, I'm going to pass out some sheets in a few minutes that are going to describe some of the basic math you need in order to do the calculations. And then I'm going to pass out a couple of sheets that also describe how we calculate the position of the sun. Then tomorrow, hopefully, we'll be able to go through the position of the moon and be able to get that pretty well down. And I don't know what we're on for Wednesday for Reagan, but after Reagan, we're going to have a share then. But in any event, I'd like to do this. And it should be a lot of fun. Anyway, speaking of fun, I know that you guys' idea of fun is probably sitting with, Gemara and figuring out a difficult taste list. And every so often I try to do that. Also, my wife sometimes starts yelling at me and saying, you got to get some exercise and whatever. So what should I do? I don't know. I don't feel like doing push-ups or anything. I get a bicycle or something. But the fact is, and I understand that you guys are, if you're very late at night, it's a difficult kind of thing. But I'd like to at least introduce you to certain important concepts in the understanding of the moon's motion. So for that purpose, my son Yitzhak is going to bring in a bicycle. And I'm going to have to ask you to move that over there. Do something. I'm 55 and a half years old. And I'm going to do something that I've never ever done in my life. At this moment, place the bar of soap down here. And I'm going to take this stick that I got purposely for this, and a piece of tape. If you think I know what I'm doing, on the edge of that tape, please. Okay. Now, bicycle wheels are very nice because they spin nicely and they're big and they arouse interest. And I bought another protractor here today. This is a real fancy one. This is actually okay. I'm going to attach this stick right over here to this wheel lock, which conveniently was placed here by the bicycle manufacturer. And now I have a stick right near the bicycle upside down on the teacher's desk. All right, now I'm going to ask for a volunteer. I don't know. You might want to ask for a volunteer to cart me out of here. But I'm going to ask for a volunteer to come up here and do some measurements on this bicycle wheel. So basically what we're going to do is I'm going to provide you with this newly invented ruler that I invented today. This here is a measuring device that happens to be a ruler, and if you actually measure, it's a foot from here to here, which conveniently happens to be about the same distance as the edge of this wheel is to there. I'm going to take this soap. I'm going to make a little mark on this wheel. Okay? All right. Isn't that nice? Okay, there's a little way. Okay, yeah, tape. I tried tape earlier, but it didn't stick so well. But the mark is nevertheless there. That stays for okay. Now, you'll never guess what I'm going to do. I'm going to start measuring angles on this bicycle wheel, right from here all the way around. And I measure the angle basically from this, which I call 0. And the line, the imaginary line, actually, which I spoke too soon. I spoke too soon. I should put it really on next to one of the spokes like that. And then we can see that there's a line going from the center up to here, and that makes an angle with this little bar here, right? So now I'm going to ask for somebody to come up here and start measuring these angles, and we can see that, for instance, if I go from an angle of, let's say, 10 degrees, move it just about there, I can then take my ruler and measure from 0 up to there, and I get a number. I get a number 0.17. Okay?
Okay, Einstein.
Huh?
You put on a spoke that's parallel with the...
What?
Not all the spokes are parallel with your line.
Right, I know, but I'm just saying this, I don't care really where this spoke is following in there. I just care about the distance this is from this line. And I'm going to go around the whole wheel and make measurements. And I'm not going to make measurements from the end of here. I'm going to make measurements straight down. So that I make, in fact, a little triangle, see like that? And as I go around making that measurement, I finally get to a point where the top of my little tape thing is 1 unit, 1 foot or whatever, from there. So in other words, when I'm at a 90-degree angle, and this thing's at a 90-degree angle to here, the height of this wheel, the height of the mark on this wheel is 1. If I'm at take my protractor again. If I want to go to a 30-degree angle, which is about there, the height of this is 0.5, a half, etc. Okay? So I'm going to go around measuring this whole thing.
Isn't it supposed to be at 45?
What?
45.
No. 45, if I go to 45 degrees, which is literally halfway up, then the height of it is about 0.7.
Is that a sign?
So you see, it's a very, as a matter of fact, this ruler that I invented conveniently happens to have on it the amount, the height of this mark for each 10-degree increment in angle that I do. If you really want to, you can come up here later, and if you still have a wheel on the bicycle, measure whatever angle you want. Let's say 60 degrees out like that, and you'll see it's around 0.87.
What are these measurements?
Okay, now I'm going to go to the board,
This sign.
and I'm going to take each of these things, since I figured out what these measurements are, and I'm going to go and graph them on the board.
For the light cycles.
Huh? Can you see okay with the bike in the way there? Okay, you can take, watch the, okay. I'm going to go like this. Here's 0. I'm going to put a little dot there. I'm going to go to 1, and that happens to 10. That was my first mark. That was the mark, that was the height of this height of the mark on the bicycle tire above the center line is 0.17. I'm going to go to 20, and the height is up to 34. I'm going to go to 30, and the height is up to, as I said, a half. I'm not putting it exactly, but there's no such thing as exact anyway. 90, as I said, when it's a right angle, it was exactly 1 foot above the bicycle tire, right? Now, if I were to go back the other way, anyone can see on that bicycle tire, if I start going back the angles farther, then I'm going to start moving to the left of the thing, and it's going to go down exactly the same way, right? So I would just go right here without even bothering to measure anymore and just say, oh, well, this next one's going to be 98, 94, 87, 77, 64, 150 is 90 plus this should be a half, etc., all the way down.
How's that half if it's 5 out of 12?
What?
It's 5 out of 12, right?
It's 5 out of 12.
It's 5 inches.
I made this whole thing 1.
It's a whole foot.
It's a fraction of a foot. Okay.
So it's
Six.
not
That bicycle tire was about is about a foot and
It's
maybe.
not
in inches. He's not going in inches.
I'm going on. No, I'm going in feet. This is a half a foot. Okay. So I'm going to go down to 34, down to 17, and at 180, when the tire has gone all the way around, so it's lying flat this way, the height is 0, right? Okay. Now, guess what? If I keep going and I start measuring downwards, I'm going to start doing the same thing coming this way. Okay? And go all the way like that. And I'm getting tired of doing this, so we're just going to stop at 270. It's going to go back to -1. Now if I draw a nice line through here, and I'm a terrible drawer, so I probably won't hit all the dots, but it looks something like this. Okay? And if I continue going on the way it should be, then I would go all the way to 360, I would come back to 0. Do that. This line, this hill, it goes up and down like this. And it's really distorted because I wasn't very even the way I spaced these guys here. But this is what they call the height of the piece of tape on the bicycle tire from that central line. It's in mathematics, it's called the sine, S-I-N-E. You often find it in books abbreviated S-I-N. It doesn't mean sin. But it's the height of the mark on the bicycle tire, depending on whatever angle it is, this is how high that mark will be. Now this sine curve is an amazing, amazing thing, because the entire world operates on sine curves. It's one of the most incredible things you can possibly imagine. For instance, light waves, they vibrate, they go up and down the same kind of way. They go whipping through zero, climbing up, and they slowly are up here, and then they go whipping down through zero again, and they're slow and up and down, up and down. The whole world, everything in the world works like this. Electricity goes up and down, back and forth, alternating current. Anything you think of nature can be is mathematically representable by a series of these sine curves. But the thing that's significant to us is we see that as we have a bicycle tire or something else rotating, the height of a particular point of it, if you look at it just from the point of view of the height of it, seems to go up and down with this kind of thing. It goes up quickly, slowly at the top, down quickly. Now, I'm going to do the next part of this experiment, and that is, I'm going to ask for a second moon guy to come and help me. And a second volunteer. Huh? Who's going to be the second volunteer? Come on, somebody, quickly. Not a lot of time. Come on, come on. All right, and I am going to be, I'm going to kindly, I'm going to move this bicycle tire. What? What? Okay. Get this tire off here. Oh, you don't even need the gloves, all right? Now, I thought you only look at it, its vertical height. It does slow down, just the same way as I did it here. As you rotate the bike, you reach these things, the height of the thing follows this pattern. Okay, there we go. All right, let's take off this stick. I don't need the stick anymore. I don't have the tape either. Okay. Now, where's my mark? I lost the mark. There it is. Okay, here's the mark. Now we saw the mark. When you look at it, it's going around nice like that. If I put the mark, if I do it just like this, and I make this little mark stick up a bit, so that it's high enough for you to see from the side, like that. And then I spin this bicycle tire. From whatever point of view you're looking, this mark will then follow the same up and down pattern as this. Let's just look at it straight on like that. If I spin it, obviously it's going to be the same thing. But if you only look at it from the side, you see that that mark is if this goes around at the same speed, at a constant speed, what's going to happen? This mark is going to go up and down according to this graph that I drew up here. You understand that? You see that?
No.
I spin this thing here. Spin it at constant speed. From the side, from my point of view, I see things going up and down. If I look at it from the side, if I measure the way it's going at the side, it's going up and down. At the top, it's taking a longer time at the top because I'm only watching how high it is. If you look at it, you see it'll be slightly longer at the top and faster as it goes past the middle. Slightly longer at the top, faster as it goes past the middle. So it follows this up and down motion. Now let's look at it sideways. If you look at it sideways, going back and forth, back and forth. If you look at it right on edge, you'll see that it's going faster as it goes right in front of you and slows down at the edges. Now, we're going to do our moon experiment again. What?
That's an illusion, right? It's not.
No, it's true. It's going back and forth, right? If you're looking at it sideways, this thing is going back and forth. It's wiggling back and forth. Huh? What?
No, it's a
Look at the
Yeah, don't look at it going around. just look at the white thing, which as it's going back and forth. Don't look at it going in and out. Look at it only as it's going back
Is
and
it an
forth.
optical illusion or it's
No, it's true.
Then what about the person standing on the other side?
What?
The person standing on the other side is going to
I see it also the same way. It's coming towards me, but as it moves according to this. It moves. It's moving in height. The height that I was measuring before is only one direction.
on both sides of it.
Huh?
Someone's watching from the other side, so when it's going slow by you, it's going slow
Yeah,
by
if he's watching from this way, it's the same. It's exactly. He's 90 degrees away. It'll be going fast for him and slow for me. Now I'm going to go do this. This is our moon guy. Where's our moon coming around? Huh?
It's the same actually moving fast and slow.
This, from your point of view, is moving faster and slower. It's just at the edge. Try to get your eyes, so you're just seeing the edge of this thing, okay? Now I spin this at a constant speed. So see if you can ignore the fact that it's coming in and out towards you, but just look at it as the white thing is just going back and forth, right? As it goes back and forth, only in that direction. I can't, it's hard to hold it. Let me go like this, okay. Huh? Okay, as it's going back and forth, even though it's going the same speed, if I look at it from the top, if I look at it right at the edge, and I just see it going, just like, it's just going like this, right? Okay, so when it goes like this, even though it's going at the same speed, it's going to follow that curve. It's going to be very, very fast as it goes by you, and then it's going to slow down at the edges, because at the edges here, if you're only looking at that direction, it's going a long distance to get to this edge here. Even though it's going the same speed, from your point of view, from it to get from here to here, it's going a long distance. It's going a long distance. Over here, it's going almost like in a straight line. But here, it's spending some of its time going inwards to me. But to you, looking at it from the side, only looking at its back and forth motion, it looks like it slows down. So it looks like if this thing is going back and forth. Now, where's our moon guy? Get your moon thing there. Okay. What? As we go around, let's take a little one. As we go around, this thing is going around also. And to the guy sitting at the center, at the Earth, who's watching this, he sees the moon back and forth as it's going around. Come around with me. Keep this thing right over here. So the orbit and Soi is as we're going around nicely, but the real place of the moon is following what this little white thing is. Now the guy is lying on his back in a nice easy chair outside. Huh? Huh? Yeah, with a warm sweater. It was really cold out. But that guy doesn't see the moon going in and out this way. He only sees it going back and forth as it's moving this way. It's going back and forth as it's moving this way. So it speeds up when it's going this way like
It's
this.
revolving around the orbit of the sun.
It's revolving around the orbit of the moon. It's revolving around the...
It has its own orbit.
It is the moon.
This is the moon, this little guy here.
What is that street?
Huh?
Going like
This
this.
is this is the
dreidel.
this guy here. The place where the center of this thing is what's called Mahala and Soi, just like we said before.
That we can measure easily. That
That's
point,
an easy thing to measure.
that
This little guy here is additionally to that thing that's speeding up and slowing down that movement. Because when I'm going this way, it's slowing down, right? Because this guy is dragging behind me. That's
How
When-
many times
when
does
the
the
white-
moon turn around?
when the white piece is right here.
Yeah,
So I don't need any extra measurements,
That's
right?
correct. Yeah, and when the white piece is right over here, you don't need any extra measurements.
So how many times does the moon turn around in 1 month?
All right, well, I'll give you all the numbers tomorrow. The Rabbi explains them in the other thing. But this is basically the orbit. So the moon is speeding up and slowing down. Now it's slowing down because it's dragging behind me, right? Now it's starting to speed up because it's going faster than my feet are going. So that's the Mahala. That's the Mahala of the moon according to the Rabbi. The Mahala Hamiti. We can discuss this. The Mahal Hamiti is the place where this little guy is, and that is speeding up and slowing down because it is adding and subtracting its back and forth movement to the constant movement of the Mahalach and Soi. Does everybody understand that? Huh?
So
Yeah.
Huh?
So you
It's
have to
like-
put the two measurements together.
So you have to put the two measurements together. Huh? What do you mean? Yeah.
You want to know where the axis, the orbits,
Oh, it's not
the
exactly
axis
the same,
of
right?
the orbit, you could know. But actually, where's the moon?
All right, so-
Another measurement.
Let me have that
On that
paper towel.
axis.
Thank you. Anyway,
So the Mahalach Mitzvah is the axis of this moon's orbit,
right. It's
and the
the,
Mahalach Amiti
is where the moon,
moon
actually
is on its
yeah.
own orbit.
Yeah.
And the sun is still going on slowly.
The moon is running around and catching up to the sun in the same way. So basically, we always go through the simplest thing, which is the picture of the Soy, easy to calculate, constant speed every day, constant speed for the sun, constant speed for the moon, and that'll tell you approximately where things are. And that's the basis for the Moila days that we have and everything else like that. That the sun catches up in this 29 days, 12 hours, 44 minutes, and 3 1/3 seconds. But the really Mahalach Amiti for the moon is dictated not only by the fact that it's off-center, the center of the circle is off-center, but there's this thing going back and forth.
What does that
Huh?
affect our view of the moon?
The moon appears to speed up and slow down much more so than just due to the effect
So it
of
doesn't do it the sun.
the off-center. No, it's just it has to do with the moon. And we need this extra precision in the moon because the moon is small and it moves very fast compared to the sun. So this extra precision that's given by having it go back and forth like this to show the speeding up and slowing down is necessary in the calculations for figuring out where the position of the moon is at any particular time. Okay, now I want to give out quickly, this is where our time is up, but if we have another 5 minutes, let me give out these sheets quickly. I'd like to, I'm happy to stay for another 10 minutes or so. If you want to stay, I understand you've all had a long day, and those who wish to stay may stay. I'll stay for another 10 minutes and try to explain some of the stuff. Let's see, these are Huh? What? Yeah, we're going to have tomorrow also. I want to do the actual calculations. All right, this is page 6 and 7. We also have page 8. Where's page 8? Okay.
Now, how do
Huh?
now according to when we find out where the position of the moon is?
Yeah.
So now, how do we know what does that affect if the Edom are going to see the moon or not?
Okay. Well, that's a good question. That's the ultimate conclusion of this whole exercise. Now you remember when those two guys are standing over there close to each other, and the moon is shining in the back of the guy's head, and the sun is shining in the back of the guy's head, so that you can't see the moon then. In order to be able to see the moon has to be separated from the sun enough so that some of the light rays from the sun are going to hit a part of the moon that we can see.
So we have to know.
I'd like to at least start with page 6 today, if we can. Page 6 is simple arithmetic. Perek Yud Aleph. Not page 6. Huh? Is everybody at page 6? All right, page 6 just tells you how to subtract and add. We've been talking about degrees, right? Everybody understands there's 360 degrees that go around the whole circle, right? In order to be more precise than a degree, we can divide a degree, you can divide it up into tenths, like 0.1, 0.2, 0.3, etc., or hundredths, you could do that also. But it's the common practice is you divide a degree into 60s, which are called, the first one is 60th of a degree is called a minute, and it's symbolized by one little slash at the top. In the Lashon Kodesh, it's called a chelik. This is a different chelik than is used in terms of determining time that we have in the idea of how when we announce the Moiled or whatever. That chelik is really, as I said before, 3 1/3 seconds of time. This is a minute of arc. What they call arc is kind of an angle. A minute or a chelik of an angle is a 60th of a degree. A 60th of a chelik, a 60th of a 60th or 1/3600th of a degree is called a second, just like in time. And then in Lashon Kodesh it's called shniyos, simply because of that. And you can even subdivide that another 60th, and then you'd have what shlishios. Anyway,
So there's Ma'ila Chelik,
huh?
Ma'ila Chelik Shnia.
Yeah. For angles, yeah. But you just have to keep separate the idea of chelik because it's used in both cases and it can get confusing. Chelik in time, we're not going to deal with chelik in time at all. We'll finish with that. The Rambam doesn't even mention it after this particular point. After starting correctly at all. Okay. In order to do, everybody probably knows how to do basic addition and subtraction in normal numbers, where you add two numbers together and then you have to go and add and carry it over the next column, etc., etc. Here you have to do it in 60s. And I'm showing you a subtraction example, how you subtract 200 degrees, 50 minutes, and 40 seconds from 100 degrees, 20 seconds, and 30 seconds. So the first thing you do is you got to start borrowing from your next door neighbor, from the next higher thing. Then you know what I mean by borrowing and subtraction?
Yeah.
Where you take 10 from the higher column and then you subtract 1 from that and you add 10 to the 1. Here you got to do 60s. First thing you got to do is, if I want to subtract 30 minus 40, I can't do that. The right-hand column, 30 seconds minus 40 seconds. I can't subtract those because 30 is smaller than 40. So I got to borrow from my next door neighbor the minutes column. I got to borrow a minute from him. How much is a minute? 60 seconds. So that gives me 90 seconds. 90 minus 40, I can finally do that, and I get 50. Then in order to subtract, I now have 19 minutes on top. So I have 1990. Now I got to subtract off 50 from 19. Can't do that. I got to borrow a degree from my neighbor, which is 60 minutes. I get 79 minutes. Now I can subtract all these things. Now I'm ending up with trying to subtract 200 from 100. From 99 now. So I have to borrow a whole going around. How much is the whole going around? 360 degrees, which is the same as 0 in going around.
We borrow that.
Huh? What?
We borrow that.
It's 60 degrees is the same as 0.
No, you can borrow because you're going around.
I don't have to borrow anything. It's
Right.
there. 0 is the same as 360. Because I'm just going around the second time. We're going around backwards. 0 is the same as 360. So I just take out 360 and add it to 99. I got 459. Now I can subtract everything nicely and everybody's happy. All right. Next thing, the Rambam says, I've mentioned several times, and I keep on repeating it. You're probably bored with me repeating it. That what we do in this hit is we have circles and we have constant speed. Rate times time equals distance. Constant speed times how much time tells you how far it's gone. If you know where it starts, then you know where it is at a future time. So you need to know the starting point. Starting point, the Rambam says, I'm going to tell you these astronomical things as they stood at a particular point during the Rambam's lifetime. When was it? Gimel Nisan 4938, which was like the very close to the first, March 22nd, 1178. It's a long time ago.
438 what? The speed of what?
No, 4938.
That was the moment the Rambam chose as being the starting point. And he's going to tell throughout the rest of Kiddush Hachodesh, he's going to tell you a bunch of things about where the sun was, where the moon was, where this bicycle tire was, all these different things. The Rambam's going to tell you where they were at the moment of sunset this day, the beginning of the day, Gimel Nisan 4938. That's what he calls the Iker. Huh? Yeah, that's what he calls the Iker. That's Halacha Tesvav and Parak Yud. Now I'm just going to do page 6 here, tell you what is